All right, so today we're finishing up 6.4. I'm just calling this 6.4 interest. And I want to remind you about a formula from pre-calc. It's A equals P times 1 plus R over N to the NT power. And remember, this has to do with compound interest. So this is the formula you use to figure out how much you're going to have at the end of an investment if the interest is compounded. So we're just going to do a couple problems with that. So let's say that $1,000 is invested. At 3% interest for 5 years. And let's say that the interest is compounded. And we're going to keep changing how often it's compounded. So for part A, it's going to be compounded annually. And of course, annually means once a year. So the idea behind compound interest is you are giving them your money, right? So what they do is, for the privilege of having your money, and they can use it for stuff in the meantime, for the privilege of having your money, they pay you some money back. That's called interest. But also, if it's compound interest, they give you money back periodically throughout the investment. So in the case of part A, it's compounded annually. So that means that even though they're going to have your money for 5 years, at the end of 1 year, they're going to give you a little bit of money called interest and to put into your account. So after 1 year, you're not going to have just $1,000 in there. You might have $1,005 or something like that. And then for year 2, you earn interest on the whole $1,005, not just on the 1,000. So that's compound interest. If it's simple interest, you just earn interest on the 1,000 the whole time. But compound interest means the interest they give you, you get interest on that interest. So it's kind of snowballs, and that's called compound interest. All right, so to figure out how much we're going to have at the end of 5 years, we just use this formula. The amount is, so P stands for the principal, the amount that you invest, so that's $1,000. And then the interest rate is always as a decimal. So in this problem, the interest rate is 3%. So the R is going to be 0.03. And then the formula has an N here and an N up there. N stands for how many times per year they give you money. The number of times they give you interest per year. So in this case, they're giving you money annually. So that's once a year. So that means N is 1. So N is 1 there. And there's another N upstairs. And then, of course, T is time, and in this case, it's 5 years. So now you just type all that in, and then you get your answer for how much money you're going to have after 5 years. So it's just 1,000 times 1.03 to the 5th power. So if you type everything correctly, it should come out to $1,159.27. Everybody good with that? Okay, so now I'm going to change it up, and in part B, instead of being compounded annually, the interest is going to be compounded quarterly. So instead of giving you money once a year, they're going to give you money every quarter. And a quarter is 3 months because 3, 6, 9, 12. There are 4 3-month periods in a year. So if you divide a year up into quarters, then each quarter is 3 months. So quarterly means every 3 months, but then that's the N is how many times they give you per year. So if it's quarterly, that's going to be 4 times a year. So the only thing that's going to change is this N here is going to be 4 instead of 1. So it's still going to be 1,000 times 1 plus 0.03 divided by 4 to the 4 times 5 power. So same formula, just the N is 4 now. So we type that in. And if you do that correctly, it's 1161.18. So you get a little bit of extra money. If they give you money once a year, it's only 1159.27. This is 1161.18. So it's not quite $2 extra, but almost. So the reason that you're getting extra money is because in this problem, when they compounded annually, the whole first year you just had $1,000 in your account. But in this problem, after 3 months, you had a little bit more than 1,000. And so then for the next 3 months after that, you were earning interest extra on the extra interest that you had in there. And then they gave you 2 payments after 6 months. So for the final 6 months, you had even more extra money based on the fact that you'd earn interest on the interest. So it kind of snowballs a little bit. Not a ton. I mean, it's only $2, but it does make a difference a little bit with how often they give you the money. Okay, so now for part C, we're going to compound monthly. So monthly is once a month, obviously. And then that would be 12 times a year. So it's 1,000 times 1 plus 0.03 divided by 12 to the 12 times 5 power. So now you can just go back and change your 4s to 12s. So I got 1161.62 this time. So it doesn't make a big difference, just about 44 cents it looks like. But it does make a little bit of a difference, 44 extra cents if they give you money every month instead of money every 3 months. Okay, so now I'm going to go to daily. And we're going to pretend that leap years don't exist, because in a 5-year period, there's maybe 1 leap year, maybe 2 leap years. So it's hard to figure out. So anyway, we're just going to pretend that all of the 5 years have 365 days. So that's 365 days a year. So that means that it's compounded. They give you money 365 times every year. So the N is going to be 365. So now I'm going to change my 12 to 365. And that's 1161.83. So an extra 21 cents if they go daily instead of once a month. Okay, now an actual bank would calculate, they would count leap years. So they would give you interest on February 29th. And I actually have a letter here to prove that. So this is a letter that I got from Fifth Third Bank. it's dated December 12th, 2009. Or sorry, no, December 15th, 2009. I want to be very accurate here. Okay, so it said, Dear Mr. Early, Fifth Third Bank periodically reviews customer account information and transactions for accuracy. It's good to hear. I'd like to know that Fifth Third Bank's checking their work, right? We want to make sure that you are aware of an error that occurred in 2008 with the interest payment on your certificate of deposit. During a recent review, we determined that the daily interest rate accrual was incorrect for accounts that were not open on February 29th, 2008. So in December of 2009, they're discovering an error that they made in February of 2008. And it was because it was February 29th, 2008 was a leap year. Consequently, you are entitled to an interest credit of 19 cents. This interest adjustment, which reflects compounding, so they gave me interest on their incorrect amount, will be reported to the Internal Revenue Service. So that means I got to pay taxes on my 19 cents. And please accept our apology for any inconvenience that this may have caused. So I've got a check here for 19 cents. I decided not to cash it. I could just show it to you guys. So real banks, they actually worry about this stuff, and they actually do make this 366 during leap years. That's if they're compounding daily. Now, a lot of them just compound monthly, so they don't have to worry about it then. But anyway, this particular CD apparently was compounded daily. Okay, so now here's what I'm going for, actually. So far, none of this has been calculus. You probably noticed that. But this is calculus. Let's say instead of giving you interest every month, or interest every day, or interest every minute, or interest every second, let's say they compounded the interest continuously. In other words, they're giving you money every moment of time. That's called compounded continuously. Now that's not actually possible because it takes an amount of time to give you money, right? So instead of compounded continuously, we're going to have a concept which is this. We're going to take the 1,000 times the 1 plus 0.03 divided by n to the n times 5 power. So this is the formula we've been using, right? And in letter A, n was 1. And in letter B, n was 4. And in letter C, n was 12. And then letter D, n was 365. So now, to go every moment of every day, I have to make n, take n and keep making it bigger and bigger, right? Now we have some notation for that. And then what compounded continuously is, keep making n bigger and bigger and see what it keeps getting closer and closer to. We have notation for that, right? LIM. So we've already started making a table for this limit. So we can continue. For part A, n was 1, and we got 1161.18. For part, that was for part A, it was 1159.27. For part B, n was 4, and it was 1161.18. For part C, n was 12, and it was 1161.62. And then for D, it was 365, and it was 1161.83. So we've already, in a sense, started calculating this limit, right? So now I'm just going to kind of cut to the chase and maybe do 1,000 for n, see what happens. So I'm going to go back and change my 365 to 1,000. And it's still 1161.83. It's just the decimals after that that are changing. So since this problem is dollars and cents, right, it makes sense to round to 1161.83. Thanks for smiling. It makes sense to round to the nearest cent. Okay, so what's happening if you compound continuously is it's getting closer and closer to 1161.83. That's what compounding continuously means. Okay, but that was method one. I really wanted to do some calculus, and so I did a limit to figure that out, right? But in pre-calculus class, you had a formula for continuous compounding. So let's pull that one out. That formula was A equals PE to the RT power. Now this formula bothers people a little bit because they kind of feel like there should be an N upstairs. Because for the other formula, there is an N upstairs. But that's just not the case here. It's an R. That is an R. It's not just my bad handwriting. It's actually an R, whereas it's an N in the other one. Okay, so now using that formula to figure out the amount, we can take 1,000 times E. The interest rate is 0.03 times 5. So you can go ahead and type that in, 1,000 times E to the power of 0.03 times 5. But I'm confident that it's going to be 1161.83, and Madison is nodding her head yes, so my confidence is well warranted. So it is 1161.83, because I knew that if I did the problem two different ways, method one and method two, I'd get the same answer. Okay, so back in pre-calc, you were scratching your head. You were like, how is this possible? How can the bank be giving you money all the time? I mean, this gesture takes at least a half a second, right? So how can they do it all the time? And then the answer is they can't. So what the concept is that what is the answer getting closer and closer to as n gets bigger and bigger? And that is what's going on here, and that is really what's going on here. They just couldn't tell you that because you didn't know what a limit was. Okay, so now I need to show you why this method is the same as this method. Okay, so let's turn to that over here. Okay, so we're just going to calculate a limit, and the limit's going to be as n goes to infinity of 1 plus 1 over n to the n power. And you might recognize this limit because it did pop up on one of the homeworks last week. But maybe not, because you might have been too tired to even know what was going on when you were doing it. So that's why we're doing it again. Okay, so we're just going to make a table and see what n, we're just going to keep making n get bigger and bigger. And I'm going to go 10, 100, 1,000. So I just got to type in 1 plus 1 over 10 to the 10th power to figure this out. That comes out to 2.594. Now I'm going to change it to 100. So put an extra 0 in my expression. .705. And I'll try 1,000. 2.717. I'm getting kind of bored with this, so I'm going to go with a million next. So add 3 more zeros. And it's 2.71828. So do you recognize this number? It's E. So that's why an E pops up in the formula, because this limit is E. And just to be a little bit more precise, the limit as n goes to infinity of 1 plus r over n to the nt power turns out to be e to the rt power. And it is possible to calculate this limit without a table. And I think we sort of got into that in 57B, maybe in BC. But anyway, we did this limit. Everybody did this limit. We just did it with a table. It is possible to calculate this limit without a table. It involves L'Hopital's rule, and it's kind of complicated, so I'm not going to do that today. But I want you to know that there, tables, you should be suspicious of tables. Is this really E, or is it just something really close to E? Well, we can prove that it's E using L'Hopital's rule, and et cetera, et cetera. So maybe another day I'll show you that. But anyway, it's E. And this comes out to E to the RT, and so that's why that formula PE to the RT is where it is. Somebody did calculus on this and found out that it was actually this. So they said, hey, we can tell non-calculus people this formula. But the problem is, then they talked about continuous compounding, and that didn't really make total sense, like how they could give you money constantly. And so now you see, oh, well, we're not giving people money constantly. It's just what it's getting closer and closer to. Everybody doing okay? So I was talking pretty fast at the end there. Okay, just one more problem, and that'll be enough for today. So let's say this would be example 2. If the investment in example 1 is compounded annually, how long will it take for the money to double? If the investment in example 1 is compounded annually, how long will it take for the money to double? Okay, so it's still the $1,000 investment. So that's the P. And the interest rate is 3%. So it's 0.03. It's compounded annually, so the N is 1. And the question is how long, so we don't know T. Okay, but we do know that we want the money to double. So what's the money going to be worth if it doubles? $2,000, because it started out at $1,000. So we want this to equal $2,000. Okay, now the algebra on this is You divide both sides by 1,000. Oh, and at this point, it would be smart for me to comment that this number and this number didn't matter, right? Let's say I had made up that the starting amount was 500. Then we would have put 1,000 over there, right? And then we would have divided and gotten a 2. So you can make up any starting number you want if the question is when it's going to double or when is it going to triple. Just like you can make up any starting number you want when the question is what's the half-life. Because you could put 1,000 here and 500 here and divide, and then you get a half, right? So I think there's problems on the homework where they don't tell you the starting amount, but they want to know how long is it going to take to double. You can make up any starting amount you want. Okay, so then when you get to here, what do you do to try to get t by itself? Natural log of both sides. So natural log of t equals the natural log of 1.03 to the t power. So we're taking the natural log of both sides. That's legal because as long as you do the same thing to both sides, it'll stay equal. Then the reason we want to do it is because when you have an exponent inside a log, it can be a multiplier in front. So the convenience of it is now this t is no longer upstairs, it's now on the regular level. So then you can solve for t by dividing both sides by the ln of 1.03. Oops, I messed that up, didn't I? Thanks for looking at me like I was crazy. Good now? So that comes out to 23.450. And that would be in years, right? So that means if you put $1,000 into an account that gets 3% interest compounded annually, 23 years or so later, you'll have $2,000 instead of only $1,000. Everybody okay? All right, that's all for today.